So I'm hoping this is a fairly short little video that deals with some aspects of heat, specifically heat capacity, specific heat capacity, and molar heat capacity. So these are three different sort of notions of heat and heat transfer. I'm going to remind you of a few things initially, and then I'm going to define those different concepts. But I hope to be able to show you by way of demonstration a few of these concepts. And I'll start right now with one of my favorite props. Well, it's a cup of coffee. Whoa, that cup is hot. Oh, can you see that steaming? Man, that is hot. That hot cup. That's why I'm supposed to use the handle, right? So anyways, I'll explain that in a moment. Okay, so heat is energy transit, energy transfer. So we typically look at it being down a temperature gradient from an object that has a higher amount of heat, higher internal thermal energy, to a substance that has a lower internal thermal energy. And so substances don't possess heat, they transfer it, and that heat is transferred due to the internal energy. So if we go back to my coffee cup, I grab it by the handle now. It has a certain internal energy. What it has a lot less of is that kinetic energy, that temperature. But the transfer was from the hot coffee inside. You can still see it steaming away. That's hot in there. It's being transferred to the container, which started out colder. But the transfer went down that temperature gradient to a substance of lower internal energy, and as the heat was transferred, the internal energy increased, and a component of that internal energy increase was the kinetic energy, so that's why it gets hotter. Okay, so that kind of nicely shows heat transfer. And the temperature, on the other hand, is a measure of the average translational kinetic energy, and so temperature is not directly proportional to the internal energy, because internal energy has two components, and I mentioned this before. One component being temperature, kinetic energy, the other component being chemical potential energy. And so kinetic energy, yes, it's hot and the temperature did go up, but there's another component that we haven't even considered at all, and you can't consider that. There's no way to really know what the internal energy of the coffee cup is, the chemical potential energy of the coffee cup, without knowing its makeup and that sort of thing. But we are already aware of that, I think. So I use the iceberg and the glass of water as an example. Obviously the kinetic energies may be similar or close, especially if you have frozen water, but the internal energy will not be the same at all because of the different amounts. Okay, so heat capacity is the first thing I want to quickly talk about, and I'll just sort of define it by way of the unit. So heat capacity is given the symbol uppercase C, that's a capital C, and the units for this are joules per degree Celsius. And so what you notice there is it is dependent on the size. So that should make quite a bit of sense to you. If 500 joules of heat energy was added to, say, a small amount of water, you would see an increase in temperature. That increase in temperature could be pretty substantial depending on the size. Well, what if you added it to a much larger amount of water? Well, you'd perhaps see an increase in temperature. You might not, depending on the size of the water, but it certainly wouldn't be as big, irrespective of the actual amount. The fact that it's much larger means the amount of the temperature change you would see would be much smaller. Okay, so what we're really looking at here is if we look at a temperature change based on the amount of energy and the heat capacity of the substance. Okay, now if I did the same thing to copper, say I added 500 joules to copper, what am I going to see? Well, I'm also going to see an increase in temperature, and again, depending on the size, I'd see a larger or smaller difference. But what if I wanted to compare these two, and now I make the amount the same? Would I see the same increase in temperature? Well, the answer is no. It's going to be different, and it's going to be different because the substances are different. And so what we have to bring in here now is this notion of, well, there's some specificity involved. So an increase in temperature would not be the same for those two substances unless we consider their specific heats. And so specific heat, as it says, is specific. Now, by definition, it's the amount of heat per unit mass required to raise the temperature of a specific substance by 1 degree Celsius. So we have here specific mass. There it is. That mass is 1 gram. Raise the temperature of a specific substance by 1 degree Celsius. There it is. That is 1 degree Celsius when it says degree Celsius. So there we have the per 1 gram, 1 degree Celsius. And so what we're looking at here is an amount of energy that's going to change. And so I can try to sort of illustrate this a little bit with this example using water. And so in the first example, part A, we transfer 4,200 joules of energy to the water, mass of 1 kilogram. And when we do that, we see an increase in temperature of 1 degree Celsius. So that's based on the specific heat capacity of water. Well, we still have water. We still have 1 kilogram of water, but now we've doubled the amount. So we've doubled the mass. And when we double the mass, we've doubled the amount of energy. And so when we double the amount of energy, add twice the amount of energy, we're going to double the temperature increase. And so that's what we mean by specific heat capacity, joules per gram degree Celsius. So based on the same substance, different amounts of heat will give rise to different temperature changes. The interesting thing is, the substances will have their own different specific heat capacities. And so just again, why do substances have different heat capacities? Well, this sort of tries to show it. I'm not going to go into too much detail here, but we look at here, kinetic energy. Remember, that's T. Kinetic energy is basically temperature. The same temperature implies the kinetic energy is the same. So in water and in copper, an increase of 1 degree would involve an increase in the average kinetic energy of the same amount, roughly. But we see a much different story when we look at the chemical potential energy, so that difficult to quantify component of internal energy. It's a little simpler in copper when it's just single atoms, so there's not as much at play in terms of interaction. There's metallic bonds, and they can be very strong, but it's not nearly as complex. The chemical potential energy gets much more complex and gets larger when you add things like intermolecular forces, and in this case for water it's hydrogen bonding, and so that's a huge one. But also when you add covalent bonds, because covalent bonds have all sorts of potential movements, vibrations, stretching, bending, all that sort of stuff, all which can either absorb or release energy. And so, not surprisingly, molecular systems typically have slightly higher specific heat capacity, and water in particular has a very high heat capacity. That's quite a large heat capacity, as you'll see in a minute. Okay, so here are some examples of heat capacities, and I'm going to use water and the glass to try to explain the coffee cup scenario again. So let's look at our water again. So very high heat capacity. That's 4.184 joules per gram degree Celsius. And so in my coffee cup I have that water with that high heat capacity, which means it has a high internal energy basically. And so it can transfer a lot of that energy and decrease its temperature slowly. That's what that means. If you transfer the energy, the temperature change is not going to occur as rapidly. So it kind of stays hot for a while, but it means there's a lot of energy in that system, in the water, the liquid. Well, it's coffee with water. And so now if I look at the cup, the glass here, it's essentially glass. I mean, porcelain glass, they're pretty close to similar. Much lower heat capacity. And so now I'm transferring energy down this gradient into the cup with a much lower heat capacity. So what's the implication there? Well, as you transfer energy, all things being equal, the temperature is going to increase, and it's going to increase pretty rapidly. It can increase to quite a high temperature. In essence, because the heat capacity is so much lower, it can almost get to the temperature of the coffee. And so that's why when you grab it, that's still pretty hot. I couldn't hold on to that very long. You can still see it smoking, but no, this is why we have handles on coffee cups. But hopefully that gets across the point that there's a lot of energy stored in water, and so when it's transferring it, it can transfer a lot of energy with a fairly low temperature change. It transfers something with a low heat capacity. That temperature change is going to be quite dramatic. It can be quite rapid and get a high change in temperature. And so that's why you see, for example, in coastal cities and places like that are on large bodies of water, the climate is a little more moderate. It doesn't have those extremes of hot and cold, because the water basically acts as a great big energy sink, and so it absorbs a lot of energy in the summertime, so it's never quite as hot, and it releases that energy that's stored, basically, and it can do that gradually, and so it never gets quite as cold because energy is being released into that colder climate. Whereas in places that are not near large bodies of water, you get much larger fluctuations in temperature. I mean, case in point, I grew up in Kingston, and Kingston, it never really quite as cold as Ottawa because of Lake Ontario and all the water there. That said, you go to somewhere like the desert, and I'm probably familiar with the idea that there's huge temperature fluctuations in the desert. You can have up to 60-degree temperature changes between night and day because there's no water around to mitigate it. The ground has a low heat capacity, so it doesn't absorb much heat and it doesn't release much heat. Now, the last one I want to talk about is molar heat capacity. And so, again, molar heat capacity, as it says, very similar to specific heat capacity, amount of heat per mole of a substance required to raise the temperature 1 degree Celsius. The unit's very similar, so this is lowercase c subscript n, and it equals the specific heat capacity times the molar mass. So if we want to find the molar heat capacity of water, well, the specific heat capacity is 4.184 joules per gram degree Celsius times the molar mass of water, 18.02 grams per mole. Low and pilled units of grams divide out, and you're left with 53.46 joules per mole degree Celsius. So that's molar heat capacity, more commonly used for gases, because it can get over or correct the problems faced with non-ideal behavior. Gases, we assume they behave ideal, but when they don't, we run into difficulties. So the molar heat capacity of a gas means you can do calculations including gas systems that are behaving non-ideally. So that's all I'm going to say about heat and heat capacities for now. So that concludes this video.